Hello everyone. In this lecture, I'm going to talk about the principles of security in computer networks, and we start chapter 8. In this chapter, we talk about the principles of network security, and also we talk about security in practice. We talk about firewalls and how to secure emails and other security related materials. So let's first focus on the question of what the network security is. To have a secure network, we have to have confidentiality, authentication, message integrity, and also accessibility and availability. So what does confidentiality means? It means that in a two-way communication between two parties, only sender and intended receiver should understand the message contents. To do this, sender usually encrypts the message and receiver decrypts it so that no one else can understand what the content of message is. And then by authentication, we mean that when sender and receiver wants to confirm identity of each other. So for example, when you enter your password to sign into your Facebook account, the Facebook web server is making sure that you are confirming your identity and no one else can access to your Facebook account. And at the same time, you should be able to confirm the identity of Facebook web server. And then message integrity means that both sides of the communication should be ensured that their messages are not altered without detection. And then obviously services must be accessible and available to users, and that is a big part of network security. This is a classic example of security attack. Look at this figure here. We have Alice and Bob on two ends of the data communication, and Trudy, which is an intruder, may intercept, delete, or add messages to this channel, and this way the security will be endangered. In the aforementioned security attack, Bob and Alice can be either two friends in real life, or they can be browser and server for some electronic transaction with sensitive information exchange between the browser and the server. And then they can be online banking, client and server, or DNS servers, or they can be routers exchanging routing table updates, or any other two parties who have a communication through which they want to send sensitive information, and a third party, in this case Trudy, may come and intercept or delete their messages or add something to their messages. So another question is, what does the third person, Trudy, do? The third person has a malicious purpose in this scenario and wants to abuse the information that is going through the connection from Alice to Bob, or in the opposite direction. And there are many different type of intruders and bad guys in this scenario. One of them is the eavesdropping attack, in which the attacker only wants to intercept messages and get more information about the sender and receiver. This is a passive attack. However, in the rest that we see here in this slide, we are talking about active attacks. Active is different from passive because in active attacks, basically the bad guy insert messages into the connection, and sometimes it does impersonation attack, which we call it a spoofing 2, in which the attacker can fake source address in packet, so that the receiver of the packet thinks that the sender has a different source address. Another way of active attackers is the ones who hijack the connection by taking over an ongoing connection, and the way they do it is they remove either the sender or receiver and insert themselves in place. And another attack can be denial of service, in which uh, the attacker prevents service from being used by others, for example, by overloading resources. One of the very famous denial of service attacks is called flooding, in which uh, many attackers in a distributed fashion send a lot of data to one single computer, one single machine, and makes it fail because the buffer of that machine will be overflowed by so many connections at the same time by so many attackers. Next, we talk about the principles of cryptography. So first, see some terminology about cryptography. The text that sender wants to send to receiver is called plain text, and this text should be received by the receiver on the other side. But if they send plain text through the connection, as I said before, intruder may intercept the messages and read them, or uh, the intruder may even alter the message. However, in order to prevent such plan, the sender, which is Alice in this case, has to first encrypt the plain text and create a ciphertext, and then it can send ciphertext without being worried about getting intercepted by the intruder. And in the receiving side, Bob has to decrypt the message. The process of encrypting the message is called encryption, in which plain text will be converted into a ciphertext, and the process of converting the ciphertext into the plain text in the receiving side is called the decryption algorithm. So they use a key in the encryption algorithm, which we call it K sub A, and another key for decryption algorithm, which we call it K sub B. Keys are actually functions which get a plain text and return ciphertext. So K sub A of M, where M is the plain text, is a ciphertext that is sent through the connection between Alice and Bob. And then in the Bob's side, the decryption algorithm is basically applying K sub B, which is the decryption key, to the ciphertext, which was Ka of M, to recover the plain text, which was M. So M is equal to Kb of Ka of M. So if you apply Kb and Ka back to back to the plain text, you get the same text message. Therefore, based on the inverse function definition, we can say that K sub B is equal to K sub A inverse, which means that the encryption key is the inverse of decryption key, or decryption key is the inverse of encryption key. Like other security solutions, the encryption scheme is not 100% secure, and there are some ways to break it. So the intruder can break the encryption scheme in two different ways. One is called brute force. The brute force means you search through all possible keys and then find out the key that is used by the receiver. And then another approach is to do a statistical analysis. We'll see some examples of these two approaches later. Also, sometimes the intruder may know both the plain text and ciphertext. This way, it would be very easier for the intruder to find out the key. For example, in monoalphabetic cipher, the intruder can simply find the corresponding letter for each of the uh, plain text letters and find the key. But, as I said, we'll talk about uh, how to break encryption schemes in the next slides. Sometimes the encryption key and decryption key are both equal. We call this kind of cryptography symmetric key cryptography. As you see here, Alice used K sub S, which is the same as Bob's key, which is K sub S, and then Ks of M, where M is the plain text, would be the ciphertext that Alice sends through the connection, and Bob simply decrypted by applying Ks again, right? So the conclusion is if you apply Ks twice on any plain text, you get the plain text itself. So K2 is equal to I, which is the identity function. Or you can say Ks is equal to Ks inverse. There are not many functions that satisfy these conditions. So choosing key, symmetric key is much harder than choosing key for asymmetric key cryptography. But in this case, Bob and Alice has to agree on the key value, and usually they do it on another connection, which is 100% secure, because if they want to agree on the key value on the same connection that they want to encrypt it, then the intruder can find out the key before you before you secure the connection. So it's better to agree on the key value on a different connection that is already secured and encrypted. So one of the simple encryption schemes is monoalphabetic cipher, the one that I just talked about. In monoalphabetic cipher, you replace any alphabetical letter with a different alphabetical letter. For example, in this case, A is mapped to M. A is replaced by M. B is replaced by N. C is replaced by B. D is replaced by V, all the way to Z, which is replaced by Q. So the first one is the alphabet in order. The second one is the shuffled alphabet, in which you have a different permutation of the alphabet. For example, if you have this kind of key, then the monoalphabetic encryption of this plain text Bob, I love you, Alice, would be nkn.s GKTC and then the rest. Why? Because B is mapped to N, so instead of B you put N, instead of O you put K, so Bob becomes NKN. Or I become S because I is mapped to S. So this is not a very difficult encryption to break. As I said before, usually they do frequency analysis, and for example, the letter S that is very frequent in English language can be decrypted simply by finding the maximum frequent or the most frequent letter in the ciphertext. And for example, letter X can be decrypted by looking at the least frequent letter in the ciphertext. So, but the encryption key is the mapping from a set of 26 letters to a set of 26 letters. Basically, to do the encryption, to find the encryption key, you have to find the specific permutation of all the 26 letters. Since we have 26 letters, the number of permutations is 26 factorial. So we have 26 factorial different encryption key for the monoalphabetic cipher. There is a more sophisticated encryption approach, which is an extension of monoalphabetic cipher. In this scheme, in this approach, we use n substitution ciphers. So we basically have n different uh, permutations of alphabets, and we have a cycling pattern of using one substitution cipher at each time. For example, look at this cyclic pattern. Let's assume that n is 4, so we have n different, we have 4 different substitution ciphers, which means 4 different monoalphabetic ciphers. The first one is called M1, M2, M3, M4, and then we apply them in this order: M1, M3, M4, M3, M2. Then this is a cyclic pattern. So after this, again, we start from M1, M1, M3, M4, M3, M2. Okay. So if you do this, then for encrypting a word like dog, you have to find the mapping of the D from M1. You have to find the mapping of O from M3. You have to find the mapping of G from M4. So this way, you cannot simply break the encryption like the monoalphabetic cipher, because in this case, you cannot apply the frequency analysis and, for example, say the most frequent letter must be mapped to S, because here we don't have one single substitution cipher. We have n different substitution ciphers, and they are applied on the plain text in a cycling pattern. So the encryption key in this example is all the n substitution ciphers plus the cyclic pattern. So we need to know both M1, M2, M3, M4 in this case, and this pattern, M1, M3, M4, M3, M2. So one of the real-world examples of symmetric key crypto is DES, Data Encryption Standard. This is US encryption standard proposed by NIST in 1993. And in this cryptographic scheme, we have 56 symmetric key, and then the plain text is encrypted by after being divided into 60-bit pieces. And using the good computers today, using a supercomputer today, you can use a brute force algorithm to break the key in less than a day. Sometimes they use 3DES instead of DES, which means using DES 3 times in a subsequent manner. Basically, you first do an encryption with one key, and then encrypt the encrypted result again using another key, and then for the third time you encrypt it with a third different key. So this will make it more secure, and it would be harder to decrypt it. Here is the general idea of DES. First, it shuffles the 64 input once at the beginning. It's a permutation. And then after the first permutation round, it does 16 identical rounds of applying a function like f on the input plus a 48 bit of key out of the 56 bit key that we have. So here is the algorithm. In each of these 16 rounds, in each of these 16 identical rounds, we choose 48 bits out of the 56 bit key that we have. Obviously, you can choose for this 8 bits out of 56 bits. In the 56, choose 48 number of times. But this is much more than 16, so there would be no problem finding 48 bits out of 56 bits. So, or choosing 48 out of 56 bits, and then after you select 48 out of 56 in each round, you call it either K1 if you are in the first round. If you are in the second round, you call it K2 all the way to K16, and then what you need to do is you divide the 64-bit input after permutation into two pieces, L1 and R1. L1 is the first 32 bits, and R1 is the second 32 bits. And then you apply a function called f, which we don't talk about the details of it, on L1, R1, and K1. And then that would give you the value for R2 in the next round, and then L1, L2 becomes R1. I'm sorry, L2 is equal to R1. So this is how you create the next 64-bit input for the next round of encryption, and then again you apply F on L2, R2, and K2 this time, where K2 is the second 48-bit that we choose from the 56 bits, and we do all of these things all the way to the last round when you get L17 and R17. And then finally we do another permutation to get the 64-bit output. The output is the ciphertext where the input was part of the plaintext. In November 2001, NIST changed its standard, and now we have AES instead of DES. AES means Advanced Encryption Standard. It is using a longer key. It's using either 128 or 192 or 256 bit keys. And then if you want to use brute force to break the key, you have to if you try it, if you can decrypt the DES in 1 second, you can break AES in 149 trillion years. So that shows how secure AES is compared to DES. Instead of having symmetric cryptography, which is private and only the two parties in a communication knows it, we can use a public key crypto. That's a completely different approach that Hellman and RSA came up with. So, in this approach, sender and receiver don't share any secret key, and the encryption key is a public key to which is known to everyone, and the receiver use a private key for decryption, which is known to itself and is not shared with the sender. So here is the scheme of public key cryptography. In the sender side, Alice used an encryption algorithm to convert the plain text to the ciphertext. And in this encryption algorithm, we only apply KB plus, which is called Bob's public key. So everyone who wants to communicate with Bob has to use his public key, which is known to everyone. So Bob put his public key public so everyone can see it. But when Bob receives the ciphertext, he wants to encrypt it, right? He wants to decrypt it, right? To get the plain text that Alice intended to send him. So when Bob wants to decrypt the ciphertext, he applies his private key, which is only known to himself, to retrieve the the plain text. So in this case, Bob's public key would be the inverse function of Bob's private key, because when you apply KB minus to KB plus, you get the identity function, because KB minus of KB plus, which will if it is applied on M, the result would be M. So that should be a identity function. So basically, the idea of this encryption algorithm is that if you know KB plus, which means the public key, if you know the public key, it should be impossible to compute the private key KB minus. So basically, as I said, KB plus is the inverse of KB minus. So we have to come up with a public function that it's impossible to calculate its its inverse function. One of the most famous public key encryption algorithms is called RSA algorithm. R stands for Rivest, S stands for Shamir, and A stands for Adelson, the three guys who invented this algorithm. I don't want to go through the details of RSA because it needs some um, uh, preliminary knowledge about number theory and modular arithmetic. So I just try to give you the basic idea. Look at this equation. A mod n to power d mod n would be again equal to a to power d mod n. So let's assume that this equation is true. In order to understand the RSA algorithm, you should know that every message, every plain text can be considered as a bit pattern, which can also be represented by an integer number. So, for example, if you have 1001001 as the message, that's the binary representation of number 145. In RSA, the public and private keys are a pair of numbers, an ordered pair of numbers. So in order to find out how to create public key and private key, we first need to choose two large prime numbers, P and Q. By large prime number, I mean each one has to have 1024 bit long if you write their binary representation, and then n, which plays a big role in creating the public and private key, is equal to p times q, which is the product of these two prime numbers. And let's assume that z is equal to p minus 1 times q minus 1, so neither n nor z are prime numbers, but obviously p and q are prime. And then obviously n is a huge number because p and q each one have 1024 bits, so you should know that obviously n must have twice the number of bits, which means 2048. And also we choose a number called e, which is obviously less than n, but has no common factor with z, which means that e and z are relatively prime. And then we choose d in a way that e times d mod z is equal to 1. So if you divide e times d by z, the remainder would be equal to 1. If you do these four operations, then public key would be n and e, this pair, and private key is n and d. Now, next I'll tell you how we can create the encryption and decryption function based on these two ordered pairs. In order to encrypt a message m, which has to be less than n, we simply need to calculate this mod, m to power e mod n. That will give you the value for c, where e and n are the ones that we calculated before. Obviously, n and e are both public, but d is not public. D is private. So in order to decrypt the message, in order to decrypt the ciphertext c, we need to first calculate c to power d, and then we have to find out c to power d mod n. That would give us the value for m, and here is the reason why, because m to power e mod n to power d mod n is equal to m itself. That's what I showed a few slides before. Here is a numerical example of RSA that you can check it out yourself. And an interesting property of RSA is that if you apply k minus first, which is the private key on M, and then after that apply k plus, which is the public key, you get the same result as when you apply public key first and then private key. Again, you can prove in number theory that k minus ok plus is equal to k plus ok minus.